In this video, I'd like to complete several examples from the semester exam review for college algebra. In class, we talked about reading through the exam design first and circling the items that may be confusing or items that you don't quite recall from class. That'll give you an idea of what to focus on while preparing yourself for the test next week. And then I also suggested the following 3 steps to prepare yourself for the final exam. So as I just mentioned, read through this outline and circle anything that's confusing or that you think you may have forgotten about. Then move on to attempting the practice problems and examples from the outline. And then lastly, watch the video walkthroughs of the exam design. So I assume that you're finished with 1 and 2 already. You've given an honest effort to this series of practice problems. So now you're watching the video walkthroughs and you're at step number 3. Some of the work that I show in these videos is probably going to be familiar to you already, so feel free to skip ahead and move around throughout the video to watch the problems that you think you may have had the most trouble with. So we talked about the vertical line test in most of the classes last week. Most of you should recall this now, but as a quick reminder, the VLT does stand for vertical line test, and that's our way of determining whether or not a graph represents the graph of a function. Now, if I can draw a vertical line at any point on that graph that violates the vertical line test, that means that a vertical line would touch the graph more than once, then that means that this graph is not a function. For part B, and this is the answer to the particular question, which graph is a function? Well, part B represents the graph of a function. And we would say so because it passes the vertical line test. And more precisely, the vertical line test is the tool that we use to verify the definition of a function. And we loosely define a function as the following. Every input of the domain maps to exactly one output in the range. And so when we were talking about this in class, we said if you selected an x value in the domain of the function, then we know that there is precisely one y value that coordinates or correlates to that. If we were to pick that same x value over here and ask for the y value associated with it, well, we've got lots of options, and that's a problem. If I choose the x value located here on the x-axis, I don't know which of these y coordinates is associated with that specific x value. And if it's not real clear, or if it's not well defined to a single value, then we don't call this relationship a function. And working with functions is important because that means solving equations have or tend to have exactly one solution, and that makes our work a little bit easier when we're looking for, quote, answers to a problem. And that's where the second bulleted point comes into play. With the graph of the function shown here, we don't have an equation to work with, but we should be able to interpret the graph to answer this problem. When we ask for f of 0, remember that would be the same as substituting 0 in place of x inside of the function, but we don't have the function written, so we're going to rely on the graph itself. So when x is 0, we're looking at the y coordinate, and in this case that would be 4. Similarly, I could ask a problem like f of -3, and that's the same thing. If we go to -3 on the x-axis, we're looking at the y coordinate associated with it, and that would be 1. In any of the if we use any x values in this window, we will only produce a single y value result, thus making this a picture of a function. Now, if we reverse that, find all x values that satisfy the equation, this is where we're working backwards, and we may end up finding multiple solutions here, and that's okay. But this time we need to find all x values so that f of x is equal to 3. When does f of x equal 3? So in other words, what x values will satisfy this equation? Well, as I scan through this graph, what I'm looking for are all x values whose y coordinates are equal to 3. So here's one right here. This x value is -2, but here's another one. This x value has a y coordinate of 3 as well. So a lot of times what we end up doing is we draw the equation y equals 3, because another way of writing f of x is y. And when we draw that equation, any points at which the that equation and the original graph intersect represent x coordinates that are solutions to the original problem. So for this particular bulleted point, these are the answers that I would expect to see. F of 0 equals 4, and x equals -2, x equals +1. Any notes or scratch work that you do on the test would be perfectly fine to leave behind. That'll share with me your thought process while trying to solve the problems, and that'll help me generate a fair score for your attempt. Moving on to the next bulleted point, I'm not going to have enough room to show my work here, so I'm going to move over to the other side, or move over to some scratch paper here. Question A, we've got x squared greater than or equal to 20 minus x. And this is an inequality, so we want to find all x values that satisfy this equation, and there's likely not going to be just a single x value or a collection of x values, but instead an inequality as a result. So I'd like to share with you a technique that we discussed in class about solving this. It was very brief during the semester, but it does depend on the graph behavior of the function, and this ties into what we were discussing in Unit 4. If this were an equal sign, let's pretend that we had an equal sign instead of an inequality, and I asked you to sketch a graph or find the solutions to this problem. Most of you would recognize that solutions exist when the equation is equal to 0, and we can find when the equation is equal to 0 by factoring. If factoring wasn't an option, then the quadratic formula would suffice. So as you recall, this factored result leads us to solutions, x equals -5 and +4, and that directly relates to the graph of this function. We have x-intercepts at -5 and +4. Additionally, the graph of this expression, x squared plus x minus 20, is a parabola that opens upward, and it goes through the x coordinate here. We could recognize, or should recognize, that the y-intercept is -20, way down here. So we've got this graph, and now let's go back to the inequality notation that we were provided with at the beginning. We were looking for the times when x squared is greater than 20 minus x. And the act of adding the x and subtracting 20 to the left-hand side does not change the direction of this inequality. And now that we're dealing with an inequality, we're asking ourselves, when does x squared plus x minus 20, or when is that greater than 0? Or in other words, where is the graph of this function above the x-axis? Now, we ended up using the factored form to locate the position and to finish the sketch of the graph, but now this is really the heart of the question that we're trying to answer. When does this graph exist above the x-axis? Well, in this region over here, the graph is above the x-axis, and in this region over here, I should have drawn a bunch of arrows, in this region over here, the the function is above the x-axis. So anything to the left of -5 and anything to the right of +4, and I should say inclusive, because the solution could precisely equal 0. But anything to the left of -5 and anything to the right of +4, that's where our graph is above the x-axis, and therefore that's the set of solutions to the original question. And I would say x is less than or equal to -5, or x is greater than or equal to 4. Consequently, we could pick some numbers within these domains and substitute them into the original to check our work. For example, if I pick a number like -6, if I let x equal -6, well, -6 is less than -5, so that should satisfy this equation. -6 squared is +36, and is +36 greater than 20 minus -6? Well, 20 minus negative 6 is only 26, so that is a true statement. If I were to pick a number, say, greater than 4, let's say that x equals positive 5. Well, 5 squared is 25. Is 25 greater than 20 minus 5? And that is true, so we know that that's a good answer. And then if I pick a number, say, in between, let's say 0. If I let x equal 0, well, now I'm looking at 0 squared greater than or equal to 20 minus 0. Is that true? Well, no, that is not true. 0 is not greater than 20, so that seems to violate our claim, which is what we expected. Any number in between these two should not support our original claim. So I'm pretty satisfied with this answer for part A. With part B, we can do pretty much the same thing, only this time we're dealing with a cubic. But it is nice that this equation was already set up and isolated so that we could essentially graph it as it is. So I still like to factor these, and I notice that x is a common factor, and we have x squared minus 6x plus 9 less than 0, and x times x minus 3 squared, or x minus 3 2 times. And I'm just imagining, at the beginning here, what if these were equal signs? Could we find where the equation is equal to 0? And that answer is x equals 0, and when x is equal to 3. Now there's a multiplicity here at 3, and we talked about multiplicity in this class. And so if we think about how that's going to affect the shape of the graph, we should recognize that while this is a cubic function whose x-intercepts are at 0 and positive 3, with a positive leading coefficient and a odd degree, the right tail points up, the left tail points down, and we have, in this case, a y-intercept of 0, which we've already kind of plotted here. But we'll also note that the behavior of this function has to exist like this due to the multiplicity and the behavior of our smooth and continuous graph in between these zeros. And so here again, if I'm thinking about using a graph to solve this question, when does this expression, when does the graph associated with this expression exist below the x-axis? Now this time it has to be strictly below, not equal to, and that begins over here in this region, anywhere to the left of 0. It cannot be equal to 0, it must be strictly less than 0. And again, we could check our work. Let's say that x is equal to negative 1. Well, negative 1 cubed is negative 1. Negative 1 squared is positive 1, so we've got positive 1 times negative 6, so that's minus 6. And negative 1 times 9 is negative 9. Does negative 1 minus 6 minus 9 represent a number that's less than 0? I think the answer there is yes. If we were to try, say, a positive 1, a number to the right of 0 that we would expect is not a solution, we would have 1 cubed, which is 1, minus 6 times 1 squared, which is minus 6, and then plus 9 times 1, which is 9. Does 1 minus 6 plus 9 represent a number that's less than 0? And the answer to that is no. So this positive 1 would not be a solution. In fact, any x value that we choose in this domain here to the right of 0 will not work or will not satisfy the original inequality. So again, on the test, or on the exam, I'm looking for evidence of work. I would suggest using this technique because we're most familiar with graphing, considering we just completed a unit on that. There are other algebra methods as well. Test points on a number line would be sufficient. We've seen that technique in the past. And if you have other correct and acceptable algebra methods, that would be fine too. Let's finish this video by talking about intercepts again. If you're being asked to find intercepts on a test, that means find both x intercepts and y-intercepts. And you should recall that x-intercepts are found when y is equal to 0, y-intercepts are found when x is 0. Now, this particular question doesn't actually specify finding an intercept. We're going to evaluate the function at a point, but the question down below associated with it does ask about intercepts. So we'll address that in just a second. Recall that f evaluated at 5 implies that we're looking for the solution to this expression when x is set equal to -5. So we'll simply execute this. And you should be able to do this without a calculator. This is showing up on the no calculator portion of the test, so the math here isn't unreasonable. It would be nice to see your work along the way so that I can follow your procedure in obtaining the result. But I think f evaluated at -5 should be recorded as 32. In the second example, our notation is slightly different. This time we're saying that f of x is equal to 14. So that's another way of saying that y is equal to 14. If the y coordinate is 14, most of the time we'll report that 14 on the left side of the equation and say that 14 must be equal to 2x squared minus 18. In this example, without a b value for this quadratic, I think using square roots to solve would be fine. But if there was a b value, let's say that this was 18x, I would suggest moving the 14 to the right-hand side and factoring or using the quadratic formula to solve. Otherwise, using algebra here would be perfectly appropriate. We'll add 18 to both sides, then divide by 2. And you've got to be very careful here and recall that when taking the square root, when indicating the square root after, or when the square root was not present in the original problem, we must be prepared for two solutions. The square root of 16 is not only 4, but also a -4 as well. If we had solved this problem by factoring or using the quadratic formula after setting it equal to 0, let's say we've got 0 equals 2x squared minus 32. Using an a value of 2 and a c value of -32, the quadratic formula would have also produced both answers as well. So question D is asking us to find the x and y intercepts of the graph. And so again, we'll recall that the x-intercept of a graph is found when y is equal to 0. So if y is equal to 0, we've got 0 equals 2x squared minus 18. And so here again, we can add 18 to both sides because there is no b value. We recognize that 9 is equal to x squared, and therefore the x-intercept is equal to both positive and -3. Since the x-intercepts occur when x is equal to positive and -3, I think the best way to report our answer is as a coordinate. So 3, 0 and -3, 0. Those are our x-intercepts. For the y-intercept, again, we set x equal to 0, and we know that there should only be one y-intercept. So the function as a result of 0 is 2 times 0 squared minus 18, which is indeed 18. And as a coordinate, we would report that as 0, -18. Now, if the question went on further, asking you to sketch a graph of this, think of all of the specific coordinates we now have. We have a coordinate at -5, 32. That could be plotted. We have coordinates at 4, 14, and -4, 14. Wait, not 14. What am I saying? Oh, yes, 14. My mistake. The y value associated with x coordinates 4 and -4. The y value is 14, so those are correct. We have x-intercepts, so 2 coordinates there, and a y-intercept. So we've got several coordinates that can be plotted, and we can generate the shape of that graph if we were asked to do so. I think I'll stop this video here, and we'll pick up with the linear equation discussion in the next one. Thanks for watching.